Well, good morning, everyone. It is truly a pleasure to be here this morning, and I do just want to thank Dr. Shano for really setting the stage for us and introducing the topic of nutrient transport. As was mentioned, I'm not Jane, but I'm fortunate to deliver this presentation on her behalf as she is one of my PhD co-supervisors. And really the topic for the presentation today is to focus on really the mechanisms behind the phosphorus transport, particularly relevant to our Canadian prairie conditions in the prairie pothole region here. So looking at some of these mechanisms, and then from that, recognizing what management practices might be particularly relevant that we can implement to address some of these potential concerns that we may be seeing. So again, the agricultural practices to reduce nutrient transport in both snowmelt and rainfall-generated runoff. And I do want to, at the outset, thank the contribution of a number of collaborators that have worked with Jane. And really in this presentation, I'll be synthesizing sort of what is our current state of knowledge in this area, drawing on some research findings, and then, perhaps looking at some management practices. And so thankful for producers, of course, who provide access to sites that can allow us to do this research, and the other contributors for their financial and technical support. Now then, by way of introduction, I guess the question becomes, why does nutrient transport matter? And indeed, why have the organizers for this conference devoted an entire day in the program to this topic? And I think it's probably not news to all of us, but we do appreciate that when we think of phosphorus as a nutrient, there is this really apparent dichotomy where on one hand we recognize that phosphorus is critically important as a nutrient to sustaining all life. However, on the other hand, we do know that when it enters into surface water bodies, it can cause particular downstream water quality impacts. Notably, of course, the explosive growth of algal and plant species, and you can see that very clearly in this image on the screen here. And so beyond the aesthetic impacts of this green color, indeed there are adverse environmental quality, water quality impacts, notably the the aquatic organisms, as they die and are decomposed, it results in the depletion of oxygen from the surrounding waters. And this causes a shift in the species composition favoring these blue-green algae, cyanobacteria. And we also see significant fish kill as a potential. And we know further that some of these species have the ability to produce nerve or liver toxins, which can further result in a risk to livestock, wildlife, or humans, even from ingesting that water. One of the most famous examples in Canada, perhaps, is Lake Winnipeg, of course, and it's an important water body, notably as it is the endpoint of most of the prairie rivers, and it is the 10th largest freshwater lake in the world. And so we've seen historically, even in the popular media, images like what we see on the screen here, where we see this impact of the cyanobacteria blooms due to phosphorus loading. And understandably, we see there are a number of stakeholders that are interested in this, notably those that participate in the commercial fishery that takes place there, or others that have interest in recreational activities. And so as such, the federal government's Prairie Water Quality Program currently focuses on Lake Winnipeg. But I do want to encourage you, as we're going through this presentation, for those folks that aren't from Manitoba, to think that a lot of the research and the BMPs that we'll be talking about are relevant to water bodies closer to home. And so maybe to have it drive home a little bit closer, maybe think about Lake Diefenbaker as an example of another water body where we're starting to see some of these water quality impacts as well, or even on your local farm, a reservoir or an area where you may have livestock drinking and that sort of thing. The unique aspect about the Lake Winnipeg watershed, of course, is that it is transboundary. And you can see that in the image here on the screen, where, of course, we know it transcends both Canada and the United States of America. And so the International Joint Commission then has an interest in understanding the sources of these nutrients across the watershed. And they use a number of tools. One of them is the Sparrow model, which is quite a powerful tool, and I think it results in some profound profound and impactful images, which is what we're looking at on the screen here. And so the color schematic relates to different loads of incremental loads of phosphorus in tons attributed to different portions of the watershed. And so you can clearly see there are certain hotspots within this from those orange colors in the diagram, notably around the Red River. But there are also a vast area where we see relatively small contributions of phosphorus entering the Lake Winnipeg watershed. And as an example, we can see even from areas such as Alberta or South Dakota, nutrients ultimately entering into Lake Winnipeg. And so then it behooves us as producers or agronomists, even in Saskatchewan or the Canadian prairies, to be mindful of these potential losses and what impacts they may have downstream. Another way of looking at this data is from some of the work by Agnes Richards with Environment and Climate Change Canada, where they've looked at the total phosphorus load entering Lake Winnipeg in absolute terms and then as a percentage of the total load and attributed to different geographic units. So if you look as an example on the scale of different rivers, the Red, the Souris, and the Upper Assiniboine, we can see that the Red River dominates at about 88% of that load. If we look at a provincial or on the state scale, we can see, of course, Manitoba making a significant contribution, followed by some of the states of Minnesota and North Dakota. But it is important to note that even Saskatchewan makes a measurable contribution at 2%. And when you look at on a national scale, we see a slight majority attributed to the USA. Within this, we're able to zoom in and examine hotspots within or smaller portions of the Lake Winnipeg watershed. And so two examples that are highlighted on the screen are the LaSalle and Morris watersheds on the top and bottom figures respectively. And so just a couple characteristics about these watersheds. The LaSalle watershed on the top is one that is relatively level topography, and it's also an area with fairly significant rural population settlement. And we also have on the bottom then, in the case of the Morris watershed, more undulating, higher relief topography. So recognizing that, let's look at how the distribution of the phosphorus load is within these portions of the watershed. And I'll draw your attention to the pie chart on the top of each of the figures. So looking at the LaSalle watershed, again, this is the top figure in that pie chart on the top. The green color relates to the agricultural contribution of phosphorus load. The blue is attributed to stream channel, and the gray area is wastewater. And so overall, we see the dominance of agriculture, of course, but if we zoom in on certain areas within this portion of the watershed that has rural settlement, you can see that wastewater dominating in certain areas. And so we can consider this as a hotspot, of course. Now, looking on the bottom figure in the Morris watershed, overall, we do still see the dominance of agriculture, but we do see in this case significant portions where stream channel and erosion may have an impact due to that increased topography and relief. And so the point in demonstrating this is to show, yes, agriculture is not the only source, but it is can be a dominant one under certain watersheds. We see the impact of channel erosion and wastewater treatment in certain portions, and these hotspots often related to sewage contribution, and then the impact of steeper landscapes making contribution from channel erosion. We do also note that there is a significant non-contributing area as well. So in our prairie pothole region of the Canadian prairies, of course, we have these potholes distributed throughout the landscape that are not hydrologically connected until we have them filling and then subsequently spilling across the landscape. And so what we see in the image here is the red area is the non-contributing area in a 1 and 2 year return period. So this is every other year. And noticeably, of course, you'll see quite a substantial portion of that total area is non-contributing. But the important part to note is that even less frequent contributions, such a 1 and 5 year return period, can have a significant impact in terms of the water quality downstream. And this is perhaps particularly troubling if we think of the potential for increased frequency of these extreme events, which may increase the risk of losses across certain land. And so then the question to ask ourselves is, are these non-contributing areas truly non-contributing? Are closed basins truly closed? And if they are not, what might that mean for how we go about managing them? This all is important to keep within the context of that average phosphorus load from agricultural land is relatively small in agronomic terms. And so we can look as an example in the case of the Assiniboine River watershed, which is outlined in red on the screen there, where the total phosphorus load per year is about 600 tons of phosphorus. And this is distributed over a watershed area of 15 million hectares. So you can do some quick math and see that the phosphorus load is approximately 0.09 kilograms P2O5 per hectare per year. And when we consider this in light of average crop removal of about 28 kilograms of P2O5 per hectare per year, we can see that that loading equivalent is approximately 0.3% of crop removal. So essentially insignificant in agronomic terms. So the challenge then for the Canadian prairies is really to resolve this disparity where we see that a potentially insignificant agronomic amount of phosphorus can have a potential impact downstream. And so on one hand, we know that nutrients, of course, are key to sustained agricultural productivity. However, agronomically minor losses can impact aquatic ecosystems. And we have to keep in mind some of the principles of hydrology and biogeochemistry and what impact those have on controlling the nutrient load and concentration. Now, fortunately, agricultural management can be a solution, and that's what we'll focus on for really the duration of this presentation. Ultimately, the discussion in this topic led to the assembling of various stakeholders in a workshop that was called Keeping Phosphorus on the Land. And really the idea is to bring a range of stakeholders from both researchers, practitioners, agronomists, environmentalists, across the 3 prairie provinces with the goal of understanding, what are the issues at play, but importantly, what are the opportunities for managing soil phosphorus, and what are the actionable areas and the knowledge gaps? What do we need to explore further through research? And all within the context of exploring solutions and not meant to attribute blame. So for those that are interested, I understand you can request a summary or a full copy of the report, and I encourage you to reach out to Jane Elliott should you be interested in that. But for the duration of the presentation, then I'll focus on some of these management opportunities that were identified through this workshop, and then even draw on some of my own research as examples of potential management practices that may be of interest. So starting with some fairly obvious examples insofar as winter application of nutrients. So we know that applications of fertilizer or manure to the snowpack can result in elevated nutrient concentrations and load in snowmelt water. Late fall applications can be a challenge as well. And so as an example, we see in the province of Manitoba where last application dates are set, which takes into account long-term data, but also the weather conditions each year. Another example is in the case of excessive soil nutrient accumulation. So essentially what we're seeing is allowing the nutrients to build up in the soil profile over time through repeated applications that are in excess to what we are seeing for crop removal. And this can result in surpluses that may be exported in runoff. So there are a couple of situations where we see this, and this is timely after the talk that Jeff just gave in the example of manure applications, so the importance of not viewing it as simply a disposal strategy, but really trying to dial in the rate to match that rate of application to what we're expecting to be removed in the harvested crop. Another example can be in the case of depressional areas in the field, which may receive annual applications of fertilizer because they're dry at the time of seeding, but then they may become flooded through some summer rains and therefore have reduced productivity as a result and poor removal of those nutrients. And so ultimately, just reinforcing the importance of doing soil testing or nutrient balances to really dial in that rate that we should be applying. Water access can be a concern where we see direct access of livestock into the water bodies can be a source of nutrients, and this occurs through direct deposition of nutrients through the fecal material, as well as the potential for stream bank erosion. So what can we do in response to this? Well, look at fencing, of course, as a physical barrier, or providing watering off-site in tanks outside of the water body to keep those livestock out of that water body. The other consideration, if possible, is to think about the timing of riparian grazing when the potential for runoff risk is less likely. There are some more subtle examples, of course, of where we can see this. The example being when you have soils with optimal levels of nutrient that can still be a potential source of nutrients in the runoff water. And so just the importance of understanding what's in the soil. So looking at that surface soil layer, a 0 to 5 centimeter depth, as this is the depth that we really expect to be interacting, of course, with the runoff water. And the question then becomes, can we draw down those surface nutrient levels without sacrificing yield loss? And we've seen some research in recent years, an example from the work of Jian Liu and colleagues, that have shown with soils with optimal or perhaps excessive phosphorus levels, the ability to draw down those nutrient loads over time through reduced fertilizer application rates and not causing a statistically significant reduction in crop yield. The other situation, though, is maybe when we even see soils that are marginal or deficient in nutrients, and recognizing that there's still a contribution potentially in the runoff water. And so what can we do in response to this? Maybe this is a case where we can look to a variable rate prescription to reduce our application rates to some of these higher risk areas of the field. And I'll be drawing on some of that later in some of my research that I'm currently working on. What about BMPs elsewhere? And so oftentimes we can even see in the farm media or reported on the news examples of success stories of management strategies for BMPs that are developed elsewhere. The trouble being that some of these BMPs developed in Europe or the American Midwest don't always translate well to our Canadian prairie condition and aren't always effective. And so we really need to consider if the practice is suitable for our conditions at the individual farm level. And the other thing is we sometimes see that management practices developed from research conducted at an entire watershed scale may not even be completely effective when applied to different areas within the watershed. And so really understanding what those localized conditions are, keeping in mind cropping systems and climate are important. So what is it that makes the Canadian prairies unique? Well, we know that the spring snowmelt is the dominant hydrologic event here on the Canadian prairies. And the reason for that is while we receive approximately 30% of our precipitation in the form of snow, it results in over 75% of the annual runoff. And the reason is it largely occurs over frozen soils where we're seeing very limited infiltration of that runoff water. And this is in contrast to summer rains received where we're typically drier soils that aren't frozen. Of course, we're seeing more infiltration until the point where those soils become saturated or where the rate exceeds the infiltration rate. So that's one consideration. The second is that we typically have ponded water over top of the soil and the crop residues. And so this can result in interactions of the water and the soil and the residue that can further result in a contribution of nutrients in the runoff water. And finally, our topography is relatively flat, so we have a relatively low risk of soil erosion in our prairies. We can then contrast snowmelt runoff versus rainfall runoff. And looking at some of the major characteristics, so for snowmelt, we see a slow rate of incident water due to melting snow, in contrast to rainfall, generally greater rate of incident water needed for runoff generation. Under snowmelt, almost zero infiltration due to that frozen soil, in contrast to infiltration greater until the soils become saturated. Under the snowmelt, we see that the particles themselves are difficult to dislodge from the frozen soil versus in rainfall, the particles may be dislodged with intense rainfall. Under cold temperatures, we see limited biological activity in contrast to actively cycling nutrients uptake due to biological activity in rainfall runoff, and diurnal variation in flow for snowmelt versus a typical hydrograph for rainfall. The question then becomes, is snowmelt important? And so I have a couple figures here on the screen. What I want you to focus on the bottom we have two different locations, or two different periods of time, I should say, relating to two locations that we're looking at. So on the left side, you can see it's labeled as rolling topography, and on the right side, you can see it's a relatively level topography with clay texture. These are two sites from Manitoba. And then we have different periods of time associated with each, where we're measuring flow on the top figure, and then total nitrogen and phosphorus load on the middle and bottom figures, respectively. And so then within each of these, we're partitioning between rainfall runoff and snowmelt runoff. And so you can very clearly see in the top figure with flow the dominance of snowmelt runoff across the majority of the time periods, with the exception of course, of a few wet years where we start to see substantial rainfall runoff. And this really carries through to what we're seeing in terms of the load of nitrogen and phosphorus, where again we're seeing in general the dominance of that snowmelt. What about the nutrient forms in the snowmelt? So again, the same two sites, the rolling topography versus the clay, the same years that we're looking at, but now we're reporting total nitrogen load and phosphorus on the top and bottom respectively, and looking at the distribution between the particulate and the dissolved fraction. And so what I really want to highlight is that we see, in general, the dissolved fraction is really dominating across both sites, even in rolling topography under our Canadian prairie conditions here. What about the distribution in rainfall runoff? And so looking again, the same two sites, same periods of time, and this time looking at, again, nitrogen and phosphorus in the particulate and dissolved fraction. Couple of things to note. First of all, in absolute terms, we're seeing the relatively lower contribution of rainfall runoff relative to snowmelt, but in this case, we're seeing that under the rolling topography, a greater dominance of that particulate fraction relative to the level clay topography. And under the clay condition, yeah, we're seeing most of it dominating in the dissolved fraction. This figure here, I think, really sums up quite nicely what we are looking at. And so just bear with me, it'll take a while to set it up, but what we're looking at here is, again, the two sites, so the rolling topography on the top, the level topography on the bottom, and then distribution of various pools from flow, nitrogen, and phosphorus load. And so when we look at flow, we can clearly see that regardless of topography, again, snowmelt is dominating, making roughly about that 75% contribution. However, when we look at the nitrogen load, we do see some contrasts in terms of what we're seeing from the sites. For the rolling topography, still the the dissolved fraction in the snow is making the largest contribution. But we're seeing notably a difference in the clay site where the dissolved nitrogen in the rainwater is making a relatively larger contribution with that white portion of the graph. And then for the total phosphorus load, we're seeing about 50% for the rolling site for dissolved phosphorus in the snowmelt, and we're seeing a larger contribution of that particulate fraction on that site of rolling topography. We also know that the winter season is different across the prairies. So we see differing winter conditions, differing snowmelt across Canada. And I just want to look at some of those differences and what makes, again, the Canadian prairies unique. So if we look at both air temperature and soil temperature at a 20 centimeter depth at two sites, one London, Ontario in the teal bars, and then two locations in Manitoba as the dark blue. And this is reporting a period from roughly October until May, October 2017 until May of 2018. And not surprisingly, what we can see in the top figure is the much lower air temperature at the Winnipeg location relative to London. What's perhaps more interesting is what we see in the bottom when we're looking at soil temperature at depth, where we see at that London location across the entire winter, we're not seeing frozen soils at 20 centimeter depth relative to Starbuck, where we're seeing significant frost penetration to deeper depth and frozen soils from roughly November well through until April. Now, what does that mean in terms of hydrology? So we're reporting discharge here over various years and two different conditions, the prairies on the left side of the figure and then various locations within the Great Lakes on the right. And so what of course stands out is in absolute terms the greater discharge from the Great Lakes relative to the prairies, but also the greater dominance of rainfall under that eastern or central Canadian context relative to the prairies. And when does that runoff occur? So we're seeing runoff in millimeters along the y-axis and then the months of the year across the bottom. And we can contrast, looking at Manitoba, where very clearly we can see the dominance again of that spring snowmelt in terms of when runoff actually occurs. And then in July, we may see a spike due to large precipitation events over the summer. But if you contrast that with Ontario, where we're seeing more frequent melt events over the entire winter season. Now looking again at phosphorus transport, but comparing the Manitoba versus Ontario. So the pie charts on the left are the same as what I showed previous, but when we look at the Ontario condition, a site with rolling topography on the top and relatively level with clay texture on the bottom. So if we compare the two rolling sites, what we notice, of course, is the increased particulate fraction in the snowmelt. And again, this is lower temperature during the winter season, those particles not being frozen and therefore more likely to be dislodged and enter into the snowmelt water. And for the clay site, we see this effect even greater relative to the prairies and a much smaller contribution of the dissolved phosphorus in the snowmelt. So now let's consider again comparing and contrasting the Ontario and prairie conditions. So both snowmelt dominated, multiple snowmelt events in Ontario, however, and the soils are not deeply frozen. So this results in very different management requirements for limiting those losses in the runoff water. In Ontario, of course, there's a need to stop those particulates from entering into the runoff water, but not as important on the Canadian prairies. And the colder winter temperatures can also result in the vegetation itself being a contributor to the nutrients in the runoff water. So when we think of these vegetative sources, oftentimes the idea behind this maybe as a management strategy, maybe to provide a physical barrier to hold that soil in place or to intercept nutrients in the runoff water. But the challenge is it may not be well suited under our Canadian prairie conditions because when the vegetation is frozen, it can release nutrients as those cells rupture. And it's very dependent on a number of factors, of course, the type of vegetation, the moisture content, and then ultimately the temperature. And so we can think of potential implications for crop choice as an example. What we are reporting here is the dissolved phosphorus release in kilograms per hectare according to different crop species. And very clearly you can see the forage or winter cereals make a significantly higher contribution of dissolved phosphorus release, and we see it going down, whereby we see, as an example, for wheat or flax, relatively minimal contribution. What about cover crops? So, of course, we hear a lot about cover crops as a management strategy, and how well might it be suited to our Canadian prairie condition? So what we're looking at in these figures here, we have different cover crop species along the bottom, and then the phosphorus release along the y-axis, and then two separate conditions. So on one hand, we have either living biomass along for the bottom two figures, or dead biomass for the top two, and then two different temperature conditions, either a relatively moderate climate, -4 to +4 C, or more usual to our conditions, -18 to +4. And so when we look at this, we can see, first of all, the increased contribution of phosphorus from that living biomass relative to the dead across temperatures, and then the increased contribution across all sources when we have colder temperatures due to those cells freezing and then subsequently releasing those nutrients. So to sum, phosphorus release from cover crops depends on the type of vegetation, the moisture content, and the severity of freezing. And when we look at edge of field study results from the Great Lakes regions, the phosphorus losses and concentrations were more strongly related to the soil phosphorus than the vegetation. And the phosphorus loss in the vegetation really wasn't found to exit the field. Now, this is in contrast to field studies from the prairies that result in increased phosphorus loss at the edge of the field. Looking at riparian buffers as a management strategy, of course, the idea behind this is to provide an alternative to cropping to the water's edge, so having that physical barrier, a less risk of applying nutrients or pesticides directly into the water body, and also, of course, providing habitat or stream bank protection from risk of erosion. The idea behind this practice is that the growing vegetation ultimately takes up the water and the nutrients in the runoff and utilizes the nutrients in the deposited sediments. And as you might expect from what we've talked about already, this is not always an effective strategy in the Canadian prairies. We can, of course, use buffers in the prairies, and they do provide that function of an alternative to cropping to the water's edge and providing critical habitat as an example. But the dormant vegetation, due to our climate, is not effective in taking up those dissolved nutrients. And the snow cover on the buffers may be less effective in retaining particulates. So the riparian vegetation, because of the temperature, can also be a source of nutrients in the snowmelt water. So if we're to look at this for implementation on the Canadian prairies, again, it can be an effective for setback and to protect the stream bank, but there's particular consideration for the type of species that we may be using in this system, recognizing the relative difference in losses according to species. Another consideration is to have a delayed harvest of that, if it's a forage crop as an example, to limit regrowth, fresh regrowth prior to the onset of freezing. And it can be a consideration to help with rainfall runoff losses if appropriately placed. So this leads me into a discussion on place-based management. And so really, drawing on what we've seen from some of these management strategies that we discussed, how might we fit them into our context? And so ultimately, recognizing that these solutions must be appropriate for the Canadian prairie climate, and not all prairie climates are the same, and unfortunately, we're faced with an expectation of potentially more extreme events. So this can make things challenging. So ultimately, some factors to consider as we're evaluating these practices are nutrients exiting the field. Is particulate transport a relevant consideration? And what cropping system are we looking at using? But ultimately, while rainfall has a relatively minor contribution, also recognizing that it can be a factor and considering that in choosing the management practice. So one of the tools that we can use, of course, is what we call 4R plus management. So again, these are the 4 Rs of nutrient stewardship: the right source, the right rate, the right time, and the right place. And we all know that this is a key tool for nutrient management planning. The benefit of this strategy is that it has oftentimes, of course, agronomic benefits in addition to benefits from an environmental quality standpoint. And so the plus component in this instance is really the utilization of additional measures working together with the 4 Rs to reduce losses. So it might be the use of different technologies, cropping choice as an example, or the stacking of management practices. And so some particular considerations in relation specifically to the 4 Rs of nutrient stewardship as it relates to snowmelt. When we think of the right time, of course, we want to do our best effort to match the timing of application as closely as possible to when those crops are going to be using those nutrients. So particular consideration for avoiding winter or late fall applications if possible. The right place, we know that subsoil application for phosphorus has agronomic benefits as well, or incorporation if broadcast is necessary. For the right rate, ultimately trying to understand the crop's demand for nutrients and then matching our application rates accordingly. And there may be an opportunity for variable rate fertilizer to minimize application to critical source areas. And so again, we saw this in relation to precision manure application as an example, and shortly I'll be showing some of my work in variable rate fertilizer application in this goal as well. And the right source. So we see emerging in the marketplace, there may be some products that are marketed as having environmentally sustainable attributes with them, or also looking at sources that have reduced solubility and therefore reduced mobility in snowmelt runoff water. And as an example of that, I'll just show a brief slide from my work where I'm looking at evaluating different combinations of phosphorus sources, rates, and placement methods in a small plot field study. And what we're seeing here is simulated snowmelt runoff, soluble reactive inorganic P, according to different fertilizer sources. And so I've defined them at the bottom of the figure there, but you can see the acronyms across the bottom for 3 different field sites that are a part of my research, and they're each situated on different landscape positions. So an upslope position, a mid-slope, and a low slope. And so we can see a statistically significant influence of fertilizer source, notably, of course, the increased concentration of phosphorus in the runoff water from application of fertilizer in general. However, one thing that we can draw our attention to is the example of rock phosphate as a relatively low soluble source, which had losses not significantly different from the control treatment. So perhaps looking at particularly high-risk zones in the landscape where we're deeming to have a high risk of losses in runoff water, consideration of a low solubility source may be of benefit. The other example from my research that I'll talk about is an edge-of-field study where we're looking at evaluating different agricultural management practices for their ability to maintain crop yield, promote nutrient use efficiency while limiting phosphorus losses in runoff water. And this work is really 2 phases of a project that was ultimately started in the fall of 2020, working very closely with the Water Security Agency to construct a wetland consolidation project at a field site near Langham, Saskatchewan. And you can see the overhead image here. What we're looking at is this field site where there's 8 hydrologically isolated basins within this field site. And you can see those outlined in the red polygons. And then the teal lines show the location of surface channels that were constructed to channel that runoff water to, as a part of a wetland consolidation study, to a permanent wetland in the middle of the property. So the 3 basins on the west side channel that runoff water into that wetland, and the 5 basins on the east channel the water to an approved adequate outlet. So once the construction was in place, we have sort of an as-constructed image looking at LiDAR data, and you can clearly see the location of the basins, of course, overlain on top of that, but the surface channel locations highlighted at the locations of those red arrows. And at each of those, we've instrumented them with weirs that are instrumented to continuously monitor flow over the spring freshet, and then we can also collect hand samples for nutrient characteristics. And the treatments that we're looking at is different management practices. So of course, a control treatment as sort of a status quo. This is an annual grain crop managed according with a fixed fertilizer application rate. We have crop residue incorporation, so recognizing what we've talked about earlier for the crop residue to be a source of dissolved phosphorus in runoff water. The idea behind this treatment is to have a light prescriptive tillage event following crop harvest to increase the interaction of that crop residue with the soil, the idea being that to perhaps increase the fixation of that phosphorus with the soil sites. We have a variable rate fertilizer application treatment with the goal really to reduce our nutrient application rates in these basin areas, especially in the bottom part of the basin where we may see elevated residual nutrient levels from that history of successive fertilizer applications, or they may be elevated in sulfates as an example, if they are saline as well. And then an annual forage polycropping treatment. The idea behind this being, can we leverage forages in a polycropping mixture, having different rooting architectures to promote infiltration of water rather than lateral movement across the landscape? And so just to demonstrate the mechanics behind the variable rate fertilizer treatment, fortunate to be working in collaboration with Croptimistic Technology, utilizing SWOT maps as a basis for informing those variable rates. And so what we can see in the middle image is their system of delineating 10 management zones within the field, which are related to different topographic positions within the field, and then also recognizing how electrical conductivity varies across the field. So in general, these red areas relate to water shedding areas within the field. The yellow areas are sort of your mid-slope locations, and the green areas are your depressional areas, the bottom of the basin. The image on the left then is just, or the table on the left is the rates of fertilizer that are prescribed for each of the zones. And so following, just to give you some information on the strategy that we use, we have different layers of fertilizer applied to these basins. So layer 2 is the third column from the left, a blend of NPKs fertilizer. And in general, what we're doing is we're increasing our application rates from the upslope locations to the midslope, where we're predicting our highest productivity in the field, and then drastically reducing that nutrient rate to the bottom of the basins where we're seeing elevated residual nutrients and also potential yield limitation due to salinity in this case. And so again, the idea is to reduce our fertilizer application rates to the bottom of those basins to see if we can't use some of the residual nutrients and therefore limit losses in runoff water. And so then how this is done is we have our polygons of our basins, we overlay that on top of the SWOT map, and then we can use commercial seeding equipment to implement these treatments. So what did we see in terms of yield? So this is 2021. We were looking at flax as the annual grain crop, and then our forage polycropping treatments. So the treatments are across the bottom of the figure: the control, crop residue management, variable rate fertilizer, and forage polycropping, and then yield. And so when we look at straw yield, not surprising that forage treatment had a significantly higher yield. Perhaps what is more interesting is looking at the treatments of grain yield, where we saw no statistically significant difference in terms of yield. And so to put it a different way, for the variable rate fertilizer treatment as an example, we had no yield penalty relative to the control by applying 90% of the nitrogen and phosphorus fertilizer. I also wanted to capture this aspect of topography, so measuring yield across different landscape positions. So 1 being those upslope areas, 2 is the midslope, 3 is the bottom of the basins, and measuring grain and straw yield. And so we can see in both instances a statistically significant influence. This was 2021, a very dry year, and so not surprising where we're seeing a yield bump in those low slope areas, likely due to improved soil moisture dynamics. What about nutrient uptake? So this is looking at straw uptake for phosphorus and nitrogen according to the treatments and the complex positions. And I just want to draw your attention to the phosphorus uptake according to the complexes, where we see a statistically significant influence with elevated uptake from those bottom portions of the basin. So I think signaling to the role that the use of this of these strategies can have in promoting uptake of those nutrients from the basins and therefore limiting the losses in the runoff water. And what do we see in the runoff water itself? So this is snowmelt simulations utilizing that intact slab technique that Professor Shano highlighted in his presentation, and measuring the soluble reactive inorganic P. So we can see no statistically significant difference. I think quite a bit of variability in the control treatment especially, but we can see in absolute terms a reduction of the phosphorus concentration from implementation of the management practices. One thing to note with this forage polycropping treatment, it is a very low concentration, but I think this is a little bit of an artifact of the sampling method where much of the residue is excluded from the slab that's collected from the field. And so this is likely a function of reduced fertilizer application rates from this treatment. However, if we look at what we actually measured in the field from the weirs that are installed in the field, we see same kind of trend overall, where reduction from the management practices, but I think the forage treatment, we're seeing that contribution of the forage residue really leveling out some of the effects compared to what we see in the simulations. And what did we see with yield? Well, similarly to 2021, no statistically significant difference in yield from the annual grain crop treatments. So for the variable rate fertilizer, similar yields despite applying about 80% of the phosphorus in this case. And so wrapping up here, what did we see in terms of these results? The straw yield from the forage treatment is highest. Of course, this is not unexpected for what we know to be true for forage crops and their breeding goals. But importantly, the variable rate fertilizer treatment yielding similar to control with reduced fertilizer application rates. We see this effect of landform complex with elevated yields from the basins, and the preliminary findings show a signal that these strategies may be effective in reducing nutrient transport in runoff water. In 22, we've seen this same effect coming forward with the differences, no significant differences among BMP treatments for the yield, and a trend for increased yield in those low-lying areas, likely a less effect in 22 from slightly better moisture conditions relative to 21. But again, this role of VR fertilizer to reduce, to have similar yields with reduced fertilizer application rate. And of course, there's a savings associated with that from reduced fertilizer costs. So the demonstrated potential of these practices to maintain yield while limiting nutrient losses, and we'll continue to evaluate this here in the next couple weeks for spring of 23. So just wrapping up the presentation in general, we can see that even a small agronomic nutrient losses can significantly impact water quality. Most of the nutrient transport in the prairies is due to dissolved forms in the snowmelt water. Many of the BMPs that are appropriate in other jurisdictions may not be appropriate for our jurisdiction due to our unique conditions. And vegetation can be a significant contributor under our climate. So the take-home message is really reinforcing the importance of these place-based nutrient management strategies with the goal of really maintaining crop yield while limiting losses in runoff water. And we need to make sure that we're validating research from practices developed or recommended elsewhere to see, are they applicable to our characteristics in the prairies? And then even on a smaller scale, can we apply them effectively within our individual farm or field, or do we need to prescribe different practices according to different conditions even within a field? And so with that, I do want to acknowledge the support of many funding agencies for my work and partners, and I would be happy to take any questions. Thank you. We have some questions coming in from text. Number one is there a way to avoid phosphorus in runoff when trying to build phosphorus levels in the soil? Great question. I think this is Oh, and I see we have a question from the floor too. Sorry, I'll get to that right away. Yeah, I think that is a very valid and relevant question. And I think I'm starting to understand this from the one slide that I showed where I'm looking at different sources of phosphorus fertilizer and how that relates to their, their ability to remain in place insofar as limiting phosphorus losses in runoff water. And I also have some data that wasn't presented here, but just looking at the impact of fertilizer application on residual nutrient levels. And so to come to the question, I think there is this aspect of looking at different sources of phosphorus fertilizer, particularly if we want to build those nutrients as it relates to phosphorus, maybe something that will allow us to have increased residual nutrient levels while still limiting losses. So some of the examples from my work, especially if we have soils of high pH where phosphorus fertility can be a challenge, some of these sources containing sulfur within them have shown to result in elevated residual nutrient levels that then can be available for the subsequent crops. So, question from the floor.
Thank you for your presentation, Blake. I was just going to ask, you made mention during your presentation that rock phosphate had the least loss to the environment, where you compare different sources of P fertilizers. I was wondering if you could comment on if that's just a first-year trend thing and what the trend of P losses from different sources of fertilizers will look like down the line. If there's going to be a flip with rock phosphate later on releasing more P losses into the environment. And then the second question would be if you could comment on if there would be any yield penalties that will be paid by choosing rock phosphate as a P source as compared to choosing other P sources like MAP and LAP, like you mentioned, in terms of losses to the environment and the yield penalties that you might pay down the line. Thank you.
Great. Stay at the mic there, because I'll admit I had a hard time hearing your first question, but I heard the second one, so I'll address that first. So I think the question was insofar as rock phosphate, so looking, what's released in the runoff water, but ultimately yield, right? Like that's what we're interested in a lot of cases, right? So it's quite interesting. We see for the 2022 field season, for my work here, peas was the crop. And so what we saw was very limited differences in yield according to the different phosphorus sources. And so really we know peas are quite good scavengers of nutrients, right, due to their rooting characteristics. So I think my answer is it's crop dependent from what I'm seeing so far. So as an example, for the peas, not really a lot of differences among the sources in terms of yield, but for the wheat, I think we saw stronger differences, but there's also the site effect as well. So I guess coming full circle, I'll give the it depends answer. But can you repeat that first question and maybe swallow the mic for me so I can hear it a little better?
Sure. So you had different sources of P fertilizers showed on the graph, and then rock phosphate had the least loss to the environment. So I was asking if that's just a first-year thing and what that trend will look like down the line. Could it be a case where the other P sources are losing their fertilizers early on, and then over time it just kind of flattens out, whereas the rock phosphate was probably losing P to the environment at a lower rate initially, and then as the P gets mineralized, there's an increased loss to the environment?
Yeah, that's a really good question. So I guess the question from what I'm hearing is losses from rock phosphate quite low in the first year is what we've seen, but does that change over time, right? So might we expect that to differ in subsequent years? So truthfully, I guess that's not something that I've looked at, but yeah, I think it's interesting to consider, how the fertilizer reaction products change according to the different sources. So yeah, something to look into further. Yep.
Thank you.
Do you still have a few? Oh, okay. Yep. Go ahead, Edgar.
Hey, Blake. Edgar Hammermeister with Western Ag Professional Agronomy. My question relates to flood events. So farmers are being encouraged to build phosphate supplies in the soil. I appreciate this is kind of a regional question, but for soils that experience the flood events, so they have melted or thawed, but now I have a flood event, what is the impact of that standing water on the phosphate dynamics? and how does that contribute to phosphate moving off of the field into our water bodies?
Yeah, great question. So, flooded situations, how does that impact, phosphorus release and that kind of thing? So, definitely something to explore further. I think what I think about with flooded soils is I think about, redox chemistry that's going on there. And so in my mind, definitely worth exploring further, but I think phosphorus maybe isn't as impacted as much by differences in the redox relative to some of the other nutrients. pH may be a driving factor. So that balanced with the fact that obviously you have interaction with the water and the surface soils and more time for release of the nutrients. So I think it would be, in my mind, confounding fact, like a number of different processes going on. But yeah, certainly an interesting question. Yeah.
Yeah, thanks for the presentation. My question is about the fact that most of our soils in the prairies are managed under direct seeding, no-till, and we know that no-till really causes a stratification of nutrients, and phosphorus does not move like nitrate. Do you think, and with your results on snowmelt runoff, with the high concentrations at the soil surface, do you think we should be revising the way that we develop recommendations for phosphorus, both in terms of the actual amount as well as the sampling depth? Can you comment on that?
Yeah, so we see this characteristic pattern of phosphorus stratification, of course, near the surface. Should we be looking at different recommendations for placement? And so I think that's an interesting question, and I think we're maybe seeing some interest, from growers. Even last week, I was in a meeting and got a question about, deep banding of phosphorus fertilizer as an example. I believe Marissa Bourgault might have a project looking at that, so it'd be interesting to see. I think, it makes sense, in terms of, limiting that potential interaction with runoff water. I think it makes sense for, just having adequate access to phosphorus as roots grow. The one thing that I will say is I think we also need to consider the current paradigm by which farmers are typically applying their fertilizer is, usually for phosphorus, seed placed, but usually in a side band. So I guess the question is, and maybe it's a chicken and an egg scenario, but do most growers have the equipment to do, let's say, a deep band application of phosphorus fertilizer? And so, maybe that's an area of interest going forward. I think, that's kind of some of the dynamics in terms of, the ability to adopt that practice. I'm not sure if it's would be widely taken up, but. Maybe one more question from the, do we have, the screen. Yeah, okay. Okay, yeah, one more question from the screen. Are you aware of differences in phosphorus fertilizers and their pollution potential? For instance, MAP with a higher concentration of phosphorus versus sources of S15 with a lower concentration, right? So I think the way that I would look at this in my study, while the fertilizer sources have different concentrations of nutrients within them, they were applied at rates such that I was only looking at 2 application rates. So 20 versus 40 kilograms P2O5 per hectare. So So what I will say, though, in response to that is, this aspect of their mobility, potential to enter surface water. And I think that is related to, based on what I'm seeing, there's the solubility of the fertilizer, and particularly, the fertilizer reaction products with phosphorus, how that impacts, soil pH, potentially on that microenvironment. So far I think it's perhaps more related to, if we're applying fertilizer at a rate, regardless of product, but just looking within the products, understanding how the solubility and therefore mobility might change. Okay, yeah. Okay, last one. All righty. Which form of soil erosion from agricultural land dominates phosphorus transport in waterways? Wind erosion causing sediment to end up in ditches or in waterways, or water erosion transporting sediment? What strategies are important for avoiding major nutrient transport in periods of high flow rate? So yeah, for erosion strategies, I'll admit that this isn't necessarily my wheelhouse. I'm wondering maybe Helen or something might have some comments during her upcoming talk. But yeah, I think I would just guessing based on what we're seeing from some of that Sparrow model, topography, relief within the landscape obviously would have an impact. And so I think on some of those higher relief areas, stream channel erosion can be a significant contributor. And so then in terms of a management strategy, I think, the importance of ground cover. And so I think, again, perhaps the regional differences, I think this is why, as an example, cover cropping is, such an important strategy in that Ontario context where, there's perhaps more of a risk of that soil erosion from the water, and perhaps not as important in terms of what we're seeing in Saskatchewan here. So, great. All right, thank you very much.